video is about helping you to solve problems that are on worksheet 3 in your packet for Unit 6. All right, the first problem we're going to go over is number 2. You might have done this one. If you have, skip forward in the video. All right, every single dimensional analysis problem that we're going to do has a starting amount and something that we're being asked a question to find. So grams, 120 grams is the starting amount here, and moles is what we're trying to find in this problem. All right, down here at the corner, I have the mole map. This is the relationship of all the units that we can convert to and from. Moles is the center unit, and you have particles and mass and volume all around it. All right, in this particular problem, we're being asked to go from mass, grams, to moles. So we're going from mass to moles. Right? The way that those two units are connected is through this connection right here, which is molar mass. Right? In other words, we're going to need to use molar mass convert. All right, let's go back up to the top and do the dimensional analysis now. Starting amounts go over 1, so we're going to write 120 grams over 1. And then we're going to use a conversion factor, and this one has to be the molar mass conversion factor. All right. Molar mass of what? Well, unfortunately, molar masses are all different from each other. They depend on what the substance is. Here, the substance is neon. So Ne on the periodic table has a mass of 20, and the molar mass is 20 grams per mole. So therefore, 20 grams goes here. It's in the denominator, so grams will cancel grams. And 1 mole goes in the numerator. Remember, in any conversion factor, the top has to equal the bottom. And that is true here. The top is 1 mole, and the bottom is 20 grams, and 1 mole does equal 20 grams. All right, when we do the math, it's like one big fraction. 120 over 20 equals 6. The unit that's left over is moles, so that's the unit. Let's do a last check for sig figs. There's 2 sig figs in this first number. The Atlantic Pacific rule says decimals absent, so zeros on the Atlantic side, as in that 0, is not significant. We need 2 sig figs. Let's make it 6.0 moles. Let's move on to the next problem. Number 4. Right here, we have moles at the beginning, and we're trying to solve for grams. Right. So in this problem, we want to put our starting amount over 1, 0.85 moles. And we want to get to grams. Well, let's go look at the mole map. We have moles. We're wanting to get to grams, which is mass. We have to use molar mass again. All right, let's use the conversion factor. We need to use molar mass again. This time, since moles in the numerator, we need 1 mole in the denominator here. And we need the molar mass in the numerator. Well, what's the molar mass? It's iodine. You think iodine's I. It's not. It's actually I2. The reason is Brinkelhoff. Remember the list of the diatomic elements. There are 7 of them. Brin, Cl, H, O, and F. They always come in 2s if they're alone. So iodine, if you see iodine alone, it's actually I2. Iodine is 127. There's 2 of them, so multiply by 2. You get 254 as the molar mass. So 254 goes in the numerator here. Let's think about this a different way. We have almost a mole. A mole weighs 254, so our final answer should be around 254, a little less than 254. When we do the math out, we get an answer of 215.9 on the calculator. The unit that's left is grams because moles cancels moles. And then we go around to sig figs. There's 2 sig figs here, so we keep the first 2. We keep the 2 and the 1, but we use the 5 to round the 1 up to 2. But $215 would not round to $22. We need to put a 0 here as a placeholder. That's the answer. So the final answer is 220 grams. That's how many grams are in 0.85 moles. All right, you might have answered half that amount if you didn't know that the formula of iodine was I2. Let's move on to the next problem. Number 10 is the next problem I'm going to do. Right, that's the starting amount, 125 liters. We want molecules, number of molecules as the end. Let's plan our trip. If we're starting with liters, we're here. And if we're going to molecules, that's particles, that's here. We have to use the 22.4 number, 22.4 to get to moles. And then we're going to have to use a second conversion factor. We need to use Avogadro's number, 6.02 times 10 to the 23rd particles to get to particles. All right, let's do the dimensional analysis. So it's 125 liters over 1. That's the starting amount. We're going to need two conversion factors, like we showed down in the conversion. There's one hallway, that'll get us moles, and then the second hallway will get us to particles. All right, the first one is this 22.4, the molar volume. So 22.4 liters. Why the bottom? So liters cancels liters. That's equal to a mole. So we put 1 mole in the top. If we stopped here, we'd be in moles. That would be a great answer, just not an answer to this question. Right? We have to keep going to particles. So the next one, we want to cancel moles. So 1 mole is 6.02 times 10 to the 23rd part. All right, the answer of all this thing is that it's 3.36 times 10 to the 24th particles. So that's the answer. Last thing we should just double check, are we actually calculating molecules of methane? I think we are, because it said 125 liters of methane, and we want molecules of methane. So particles here is, in fact, molecules. So sanity check, it works out. Remember, parts is parts, though, so if we wanted to calculate atoms, yeah, that's a particle, but we're not talking about methane then. We're talking about how many atoms are in methane. All right. Next problem is the last one on worksheet 3 that I'm going to go over. It's not a circled one. It's number 16. This is kind of a complicated problem, which is why I chose to do it. You should probably try to do this yourself before watching this video. The reason it's complicated is because it has a starting amount, but then it asks how many molecules. Well, how do you go from molecules to molecules? That should be the question. Well, the deal is it's really two problems in one. It's how many molecules will an equal volume of H2 calculate. So in other words, we're starting with 1.0 times 10 to the 23rd particles, molecules of neon. But at the end of this whole thing, we want particles of H2. How many molecules will an equal volume of H2 contain? So that's where the complication is. So we have to go through volume. So an equal volume, so we need a number, we need an answer for the number of liters of Ne, and then we're going to plug that back in, and that'll give us the number of, for the number of liters of H2, and then we're going to solve back to particles H2. So let's do this thing. One more time, we're solving going particles to liters, and then we're going to use that same number for H2, and I'm going to go back liters to particles. All right, let's do this thing. So particles to liters, we know that 6.02 times 10 to the 23rd particles are in 1 mole. And then we know that there's 22.4 liters in 1 mole. So we get, at the end of that, particles cancels particles, moles cancels moles. We get that this is 3.72 liters of neon. Well, if we want the equal volume of H2, we start with 3.72 liters of H2, equal volume, and then we're going to do the same math over again. 22.4 liters. Wait a second. That's a mistake, because liters has to cancel liters, so this time it's on the bottom. 22.4 liters is 1 mole. That'll get us moles, but we want to go back to particles. So we want 1 mole in the denominator and 6.02 times 10 to the 23rd particles in the numerator. All right, and that'll give us our answer. Well, guess what it is? It's 1.0 times 10 to the 23rd. Why the heck did we have to do all that math? I want to point out to you that the number 22.4, I should probably use a better color for this. 22.4 liters is here, and 6.02 times 10 to the 23rd particles is here. It doesn't matter what substance you're talking about. The molar mass, it does matter, the substance. So this hallway is different based on different substances. But these two hallways aren't. And we only went down those two hallways. So we should get the same answer. It really shouldn't matter whether we have neon or hydrogen here. All right, that's number 16.